I'll introduce Mackenzie here quickly. So Mackenzie Rathgeber has been with Perennia for almost a year as our agriculture environmental specialist. Mackenzie is near completion of her graduate studies in animal science from Dalhousie Agriculture Campus. Mackenzie's research looked at how improved rotational grazing management may enhance soil carbon sequestration and animal performance in maritime Canada. Today, she's going to give us some insight into this rising new concept. Thanks for joining us, Mackenzie.
Thank you. Hi, everyone. I'm Mackenzie, as Rosie said, and I'm excited and happy to talk to you today about improved grazing management to enhance soil carbon sequestration. So just a bit of an overview of what I'm going to cover today. I'm going to approach it sort of as a little bit of a storytelling. So I'm going to spend a little bit of time talking about climate change and livestock. And then I'm going to cover a bit about soil carbon and how it moves through the environment. And then I'm finally going to get to why grazing and why improve it. How does it relate to soil carbon and livestock? And then I'm going to finish with touching on some of my research and what sort of opportunities does Atlantic Canada have for this concept. So this is not news. Climate change is happening. The recent findings of the Working Group 2 to the IPCC 6th Assessment Report confirmed significant impacts climate change is and will continue to have on agri-food systems. 10% of the currently suitable area for major crops and livestock are projected to be climatically unsuitable by mid-century under high emission scenarios. Increased potentially concurrent climate extremes will periodically increase simultaneous losses in major food producing regions. So it's only going to get harder to grow food. The pressures of implementing best management practices to enhance greenhouse gas mitigation and reduction and create resilient and sustainable ecosystems will only continue to grow. And on top of that, we're faced with the challenge of producing food for a growing global population expected to reach 8.5 billion by 2030, 9.7 by 2050, and 11.2 by 2100. And with this growing population, there will be an increased socioeconomic status and urbanization, expecting to increase global demand for meat and dairy by 57% and 48% between 2005 and 2050. So sort of a global look at things, but it's safe to say we're faced with some challenges. And another sort of global look. So livestock are important not only economically, but where it accounts for about 40% of agricultural gross domestic product, employs 1.3 billion people globally, creates livelihoods for 1 billion of the world's poor, but it's also significantly important for human health. It provides valuable source of micronutrients, 18% of global caloric, and 25 to 30% of protein consumption by humans. The FAO found an inverse relationship between the inclusion of animal-sourced foods and in the human diet and the global hunger index. So as soon as you start taking livestock out of the picture, you're seeing more hunger. And lastly, not to dwell on this too much, but there was a study that looked at a simulated removal of livestock from the human diet in the United States, predicted to result in excess dietary energy and increased nutrient deficiencies for American consumers. So livestock and climate change. I'm sure many of you, if not all of you, have heard this statistic, which I guess is getting a little bit older now, but the FAO estimates globally that livestock represent about 14.5% of all anthropogenic greenhouse gas emissions, with cattle contributing nearly 2/3 of this. This is significant. We are well aware of the environmental impact that producing livestock for food has. However, something maybe not as emphasized is that this is one statistic. It is part of the story, but it's only one part of the story. When looking at environmental footprints, I think it's important to acknowledge all sustainability indicators. So while this includes greenhouse gas emissions, it may also include nutrient balance, land and water use efficiency, water quality, carbon storage, and biodiversity, and other possible ecological services that I did not list. And just to build upon this, there has been, it seems to me, whenever I talk about the work that I do, the question about livestock and their sustainability comes up. And again, something maybe not, something overlooked is the nutrient density of livestock foods. And to relate this to greenhouse gas emissions, this one paper was that came out of Western Canada was looking at the sustainability of Canadian the Canadian livestock sector, and they found that animal-based food have shown to consistently have lower emissions on an intensity basis for energy, protein, or overall nutrient density on a per weight basis. Assessments of the role of meat and milk products in a sustainable diet are often based on greenhouse gas emissions expressed as calorie of food produced, leading to the conclusion that livestock have a greater negative impact on the environment than, say, plant-based diets. Again, this approach is looking at maybe calories are more important than dietary protein. And that leaves the limitation of just using a single metric to assess environmental impact of food products. So it's important to consider the production system as a whole, which leads me to this slide. So yeah, so the FAO pegs that we need low carbon livestock. And 5 practical actions that can be widely implemented for measurable and rapid impacts on livestock emissions include boosting efficiency and resource use, intensifying recycling efforts, capitalizing on nature-based solutions to ramp up carbon offsets, which I've highlighted here because that is my focus for today, striving for healthy, sustainable diets, and developing policy measure to drive change. So carbon offsets, how does this work? So this is referring to the natural carbon cycle and how we may enhance, manipulate an ecosystem to favor sequestration rather than emission. So first, we must have a general understanding how carbon moves from the atmosphere and into the soil and vice versa, because it is a cycle. And yeah, I have a diagram here that just shows sort of the basic movement. So you've got CO2 in the atmosphere that is sequestered through the vegetation, through photosynthesis, and it moves into the soil through different mechanisms, and eventually that carbon may be respired and released back into the atmosphere. So to get into more of that, so how is soil organic carbon formed? Well, it is directly related to the amount of organic matter contained in the soil, and organic matter in the soil results from both the growth and death of plant roots, and indirectly from the transfer of carbon-enriched compounds from roots to soil microbes. So it equals soil microbes, including bacteria and fungi, decaying material of previous living organisms, plant and animal tissues, fecal material, and products formed from their decomposition. So when carbon inputs and outputs are in balance with one another, there is no net change in soil carbon levels. When carbon inputs exceed carbon losses, soil carbon levels increase over time. So drivers of soil organic carbon sequestration. First driver that I'm going to talk about is net primary productivity, as it's the main driver of sequestration. About 60% of net primary productivity is allocated below ground. So below ground carbon inputs are extremely important when it comes to soil carbon sequestration, as they're more often incorporated into carbon than above ground inputs due to their chemical composition and their presence in the soil. Additionally, root carbon inputs have a soil organic carbon stabilization efficiency that is on average 5 times greater than above ground carbon inputs. This makes the root system of a grassland ecosystem in particular incredibly important when you're considering soil carbon sequestration. Fungi and bacteria also play important roles in soil organic carbon accumulation and stabilization, but also respiration too, so your loss of soil carbon. Climate and climate change regulate metabolic activity of microbes, influence net primary productivity, so your main driver with just photosynthesis, and your soil type and conditions can also influence carbon sequestration. Just a touch on this, plant diversity can also enhance storage by elevating below ground inputs, promoting microbial growth, turnover, and entombment of necromass. So soil carbon is distributed between different fractions in the soil. You have your particulate organic matter, your mineral associated organic matter, and a small portion as dissolved organic matter. So particulate and mineral associated organic matters differ in their formation, physical and chemical properties, and their mean residence times in the soil, or their recalcitrance, which is just resistance to decomposition. So the particulate organic matter is fragmentation or plant and microbial residues. They are less resistant to decomposition. Usually residence time is years to a decade in the soil, where your mineral associated organic matter are single small molecules leached from plant residues or exuded from plant roots, and they associate to minerals directly or after microbial simulation as microbial necromass, which is just dead microbes. So root exudates are a key pathway to mineral associated organic matter formation. This form of carbon is more resistant to decomposition, has a residence time decades to centuries, as there's strong chemical bonding to minerals and physical protection in fine aggregates. So does this mean more roots, more soil carbon? So about 46% of root exudates, 9% of root tissues, and 7% of above ground carbon residues are transformed into the mineral associated organic matter, and about 19% of root litter is transformed into particulate organic matter. So these are just approximate numbers, but basically what you can get from this is that plants with greater allocation to roots contribute more to soil carbon sequestration, particular to the formation of mineral associated organic matter, which has longer residence time in the soil. However, it remains largely unclear how the contributions of roots, so root exudates and root litter, and above ground inputs to soil organic carbon accumulation change with grassland types, soil properties, and climate conditions. Which brings me to grazing. So why grazing? Well, there's great opportunity and globally there's a need to restore grassland ecosystems. Grassland ecosystems cover an area of approximately 52.5 million kilometers square, accounting for about 40.5% of the Earth's land surface, and about 34% of the terrestrial soil carbon is stored in grasslands, with 90% of their carbon stored below ground as root biomass and soil organic carbon. Grasslands are vulnerable to human disturbance and climate change. So there's been severe decreases in biodiversity and ecosystem functions, resulting in reductions in soil organic carbon storage. This is looking obviously at a global overview. I will get into maritime Canada. So livestock are natural residents of the grassland ecosystem. Improving the way they interact with the system will have influence on how the soil carbon may accumulate, stabilize, or cycle back into the atmosphere, among other things. So again, why improve it? Well, grazing livestock can be used as a tool to build soil organic matter and provide ecological services to an agri-ecosystem. Soil organic matter is directly related to soil carbon, as I've already talked about, which will enhance natural carbon sinks. And you can also utilize and improve marginal land for food production. As well, improving your grazing management will improve or increase, so firstly, your soil carbon and stability, and your soil organic matter, which will improve your water retention and infiltration, your nutrient holding capacity, will increase your plant biomass, your biodiversity, resulting in an extended grazing season. Your grassland will be more resilient, which is especially important with climate change. Your food web structure will improve and your soil structure. There might be more that I'm missing. So how do we improve this? Well, livestock grazing involves the interaction of livestock, vegetation, soil, water, and human decisions. So this all results in ecosystem structure and functional changes. So when looking at general grazing management, there are several key considerations. The number of paddocks per herd, your stocking rates and densities, which is your grazing intensity, provision of planned post-grazing recovery periods, your vegetative growth, and seasonal impacts. Which brings me to the concept of adaptive multi-paddock grazing, which is a form of rotational grazing, but with high stocking densities and long recovery or rest periods for the pasture. The idea is that there's an adaptive component to this style of grazing management, where the grazing schedule and method are not necessarily always the same. You adapt and change it to the changing climate and grazing conditions in order to maximize forage utilization and minimize plant or soil damage by overgrazing. So this method is intended to be variable in nature, as a grazing system is dynamic, and therefore you shouldn't always be doing the same thing to varying conditions. It's not going to be optimal. So functions which facilitate improvements with this concept, while you're preventing overgrazing, which maximizes growth potential and net primary productivity, as you're preventing grazing of new vegetative growth, because the animals are moving quick enough that you're preventing them from taking that second bite per se. You're preserving the root system as there's minimal disturbance. Again, you're not overgrazing it, so you're not shrinking that root system. There's minimal soil erosion and compaction, which ties into the root system. And you're leaving residual vegetation, which maintains plant cover, which is important for soil health. You also are going to be getting some hooving actions with the higher density. There's going to be a bit of a trampling effect, which will help incorporate residual organic materials into the soil, but also just get the soil moving. And you're going to get an even graze. The livestock theoretically should more efficiently utilize all the biomass in their area because they have less room. They should be less picky. And that also results in a more even distribution of manure and urine, which is a direct return of nutrients to the ecosystem. So does this actually work? Here are two examples from the southeastern USA, specifically looking at adaptive multi-paddock grazing systems compared to just continuous grazing systems. And they found more standing crop biomass, almost 50% higher pasture photosynthetic capacity, almost 20% reduction in soil carbon respiration rates, a 20.5 increase in soil organic carbon, specifically in the top 10 centimeters of the soil profile, and also regeneration of soil food web population, structure diversity, and biological functionality. And then the other study, also comparing A&P grazing to continuous grazing, found that soil carbon stocks of 1 meter's depth were over 13% greater than continuous grazing, and significantly more standing crop biomass and higher water infiltration rates. Which brings me to Atlantic Canada. So for my master's studies under the supervision of John Dinesfeld from Agriculture, Agri-Food Canada, we're looking at grazing intensity and how soil carbon may change for these 3 different treatments. The trial is at the Nepean Research Farm. So the 3 grazing treatments that we looked at were pegged high, medium, and low. The high were moved 3 times a day. Technically, they were manually moved once, and we had automatic gates that moved them the other 2 times. The paddock sizes were variable, so this treatment had sort of the adaptive component. The area was calculated depending on the forage available through dry matter samples. And the medium, the animals were moved every 4 days with a permanent set paddock size. And low, they were moved every 8 days, again with a set paddock size, but more area. And I estimated the soil carbon change using the HOLOS life cycle analysis model that was developed by Agriculture and Agri-Food Canada researchers out of Western Canada, that is intended to help Canadian farms understand and estimate where their emissions are, their source of emissions on the farm, but also sinks. So I looked at 3 grazing seasons. So for net carbon sequestration per hectare, as you can see on the graph here, the high grazing treatment had a higher average net carbon sequestration per hectare than the low or medium, and the lower medium did not differ from one another. The interaction effect showed that the high grazing treatment is overall better at sequestering carbon in 2020 and 2021 than medium or low any year. I will mention too, another interesting fact was the high grazing treatment actually had a full additional rotation. So there was significantly more standing biomass. And then inversely, the net emissions per animal per day, the high grazing treatment had the lowest average net emissions per animal per day than the medium or low, due to the carbon sequestration, which offset the emissions. As you can see in the gray for high, and then the blue and orange are the low. The low and medium, again, did not differ from one another. Yeah, so I'm not complete yet, so I wouldn't run away with this information, but it certainly shows good potential for adoption of this improved grazing methodology for soil carbon. So just some takeaways from my presentation today. The pressures of incorporating more best management practices to help mitigate greenhouse gas emissions amidst a changing climate will only continue to grow, and improve grazing management to adapt to variable growing conditions to maximize primary productivity and minimize soil and root disturbance can help enhance soil organic carbon sequestration. And there is promising opportunity for Atlantic Canada. And thank you for listening.
That was great. Thank you, Mackenzie. We have time for a few questions before we move on to Ed Bork. Please type them in the chat. I know I've got a couple of questions. Pretty much on your last slide there, you said that high intensity grazing reduced net emissions per animal per day because of increased carbon sequestration. So were there any reduced methane emissions from the cows based on improved forage quality, or was it all because there was higher biomass in the pasture?
Yeah, there was no significant difference in methane emissions between the different treatments. So that the way that I manipulated the data there, yeah, that offset was due to the sequestration that the model estimated.
I see. And then, rotational grazing is the off-calf BMP that I am the least familiar with, but I have worked with it a little bit. So from what you say about AMP, it sounds like it involves a lot more management decisions, because you're making a management decision based on growth of pasture. So what is it? Does it make it harder to actually develop a grazing plan?
I think that it's adaptable in nature. So I think that you can make it what is realistic for you. And I think that's the idea. So to answer the question, possibly. Yes. And I think that's definitely a concern that seems to arise around the topic for sure. But yeah, I think it's more so about the principles of preventing overgrazing and utilizing your forage to the best of your ability is sort of what I would like to highlight, I guess, with that sort of management.
There's a question here in the Q&A. Is there any way to estimate the soil carbon sequestration potential or maximum amount of carbon uptake using the Holos model?
Yes, you could. If you know your plan and you have, depends on what information that you have, you could get a rough estimate, yes.
And then another question, what dates or season is the grazing plan? Is there any study available on winter grazing that you know
of? So that's specifically to my study. It was May to late October. 2020 was not a great year for data, just with the challenges of COVID, but 2021, like I mentioned, the high grazing treatment actually had a full extra rotation because there was that much more biomass available. So that was really interesting to see.
Great. Allison, I think we'll also ask that question to the panel here shortly. Another question, how did animal performance compare between grazing methods / weight gain per animal per day?
Unfortunately, there was no significant difference for that. I'm still yet to look into why that might be, but yes, there was no significant difference.
Great. Okay, we are going to move on to Ed. If you're ready, Ed, I'll just introduce you, and then Mackenzie, don't go anywhere. We'll invite you back for the panel. Okay. So Edward Bork is the Mattheis Chair in Rangeland Ecology and Management and Director of the Rangeland Research Institute at the University of Alberta. He has been teaching and conducting research for more than 25 years on basic and applied topics, including integrated weed control, grazing systems, fire ecology, forage production, agroforestry, and recently the role of rangelands in providing alternative ecosystem goods and services, including carbon storage, greenhouse gas reduction, and biodiversity retention. He has supervised 48 graduate students, including 11 PhD students. Dr. Bork maintains close ties with the agriculture industry and has given numerous extension talks. Thank you so much for joining us, Ed, and I'll let you take it away.
Thank you, Rosalie. Good afternoon, everyone. You can hear me all right?
Yes, we can.
Okay, very good. I realize you've had a very long day with a lot of information coming at you. So I'm the last speaker of the day. Hopefully I don't chase too many people away. I'm actually going to build on a lot of what Mackenzie was presenting, and I'm going to try to share with you some of the results that we've been finding with some of the grazing work, including specifically on adaptive multi-paddock grazing out in Western Canada. And I think the results, long story short, the results are really good. I think the livestock industry and the beef industry in particular has gotten a lot of bad rap over the years, particularly where we have grazing on public land, with folks saying we should, eliminate grazing, that grazing is deterring or detracting from the environmental goods and services from that land area. And I think the work that we're doing on carbon and greenhouse gases is showing at a minimum grazing is compatible with not only maintaining that carbon and even increasing that carbon, and adaptive multi-paddock grazing has the potential to further increase that carbon. So I'm going to attach some data to these ideas, and then we'll build on that. And I want to recognize that this is not just my effort. This is a lot of scientists, a lot of masters and PhD students and postdocs and visiting scientists that have participated in this. And we've been doing this for roughly 10 years now. So we've actually made a lot of progress on this front. Okay, I just want to start by sharing with you our overarching research program objectives. So as I said, we've been doing this for 10 years now. We started out with a real simple question of trying to quantify the size and stability of carbon stores in our northern temperate grasslands. So we wanted to look at how much carbon is in the soil, in the organic matter, in the vegetation, in the litter component, how much is above ground versus below ground, and so on. We wanted to know whether and how grazing increases or decreases this carbon. And the reason for that is because we want to have a predictive framework for understanding where, when, and how grazing alters carbon. Because if we're going to have some kind of mechanism to reward producers for enhanced carbon storage and therefore climate change mitigation, we need to have the data to back that up. And so we need to have insight into the mechanisms responsible for those carbon changes. And my goal all along has really been, as I said, to build that empirical foundation that can be used to reward grass farmers or ranchers for carbon storage. Okay, why soil carbon? So I think Mackenzie did a pretty good job already outlining this. I just want to kind of orient people as to where the carbon is. And when we look at atmospheric carbon, which is really what we're worried about, we're looking at about 800 gigatons of carbon. So 1 gigaton is 1 billion tons of carbon. The reason why this terrestrial carbon pool is so important is because it's actually about 3 times the size of the atmospheric carbon pool. So 800 gigatons in the atmosphere and nearly 2,400 gigatons in soil carbon. So if we can increase soil carbon even by 1 or 2% through a land use management change, that could have a really profound impact in offsetting some of that rising atmospheric CO2. And of course, we know what the source of that atmospheric CO2 is. Most of it is due to human emissions. Here's this 9 tons that we're emitting. And interestingly enough, the enhancement in atmospheric CO2 is offset at least partly by enhanced plant production. So enhanced photosynthesis of plants because they have access to more CO2. And I've had producers say, well, my pastures are more productive because of that rise in CO2. That may be, but it's not enough to offset the total increase in CO2 due to fossil fuel burning. Hence the need to find ways to basically sequester more in our terrestrial systems. And grazing is one of those vehicles that we have available to us. So we started out, and I'm going to go through a series of studies here, but I'm only going to present to you snippets of the results. So I'm kind of high grading the results here. I'm leaving out a lot of details. We started out in 2012 asking this fundamental question of how does grazing impact grassland soil carbon and how much soil carbon is there? So we sampled over 100 sites in Alberta. You can see them distributed across a really large area, a really large agroclimatic zone as well. So brown soils, black soils, dark brown, low rainfall, very arid, all the way through to mesic, highly productive, high organic matter, all the way down to low organic matter. And we generally looked at these grasslands both under long-term ungrazed conditions. So this was within long-term grazing exclosures maintained by the Alberta government, and also outside. So we had a chance to compare that. And when we did that, we were very intrigued to find that soil organic carbon was actually higher in the areas, in the grasslands that were continued to be subject to long-term moderate grazing. Now, the caveat here being moderate grazing. So in this exclosure here, this is west of Calgary, you can basically see that there is evidence of grazing, but it's not really heavy grazing. It's kind of that average moderate grazing that the Alberta government allows on their public land base. But even that grazing regime led to 12% higher carbon. So that was very intriguing to begin with as a first indicator. We also lucked out and came into possession of some carbon data from grasslands in Saskatchewan. This is, again, across a very large number of community pastures and paddocks. This is from 33 paddocks distributed across the mixed grass prairie in Saskatchewan. And they had collected all of these soil samples, didn't know what to do with them, ended up sending the results to us, and we did an analysis of that data. Now, what was different here from the Alberta data set is we had long-term cattle stocking rate information. So we knew for each pasture exactly how many cows or yearlings or cow-calf pairs were turned out on what date and when they were removed. So we could use that to compute long-term cattle stocking rates for each pasture over an extended period of time. And when we did that, and when we looked at the relationship between carbon mass and what I call the long-term mean normalized stocking rate, and it has to be normalized because areas that have slightly higher rainfall would have higher production because more moisture, more plant growth, and therefore more carbon. So we had to adjust that for normalized stocking for the region. When we did that, we found that there was, again, this positive influence of grazing on soil organic carbon, largely constrained to the top 15 centimeters of soil, so where most of your organic matter and carbon is located. And we also found, and I don't present it here, but that this was accompanied by changes in plant species composition. In particular, there were certain agronomic grasses that we found had invaded, and because they were grazing tolerant, were very prevalent within those areas, having higher stocking, and that was the key to triggering this increase in soil carbon within the top 6 inches or 15 centimeters. So again, all of this is pointing towards grazing being compatible with not only maintaining soil carbon, but increasing soil carbon over time. Now, in our benchmarking work, we also did some a comparison of different land uses. So if you look at this graph here on the right, we looked at the mean carbon mass in tons per hectare between native grasslands. So these are areas that had never been plowed, In some cases, they had naturalized, so invaded agronomics that had blended in with the native vegetation. But then we compared that to areas that had a history of being cultivated at some point in time, and they'd either been planted to tame forage in the past, or they were continuing to be managed for annual crop production. So barley, canola, wheat, pulses, whatever the case is. A couple things really jump out here. The first one is that if you look at the different land uses, you see that anything that's been cultivated in the past has much lower carbon mass, upwards of 40% lower carbon. And this is consistent globally with what you find, is that if you take these long-term perennial plant communities and you cultivate them and you subject them to repeated cultivation, you will lose anywhere from 30 to 55% of the soil carbon. So now, when we look at the native grasslands themselves, so these are areas that had continued to be subject to long-term grazing, we found an average carbon tonnage. And this does not include the deep carbon, by the way. So this is only 30 centimeter soil depth and above, including roots, litter, organic matter, live vegetation, and so on. We were around 90 tons per hectare. But the range extended from about 50 to 60 tons of carbon per hectare in our driest environments. This picture here is from the dry mixed grass prairie in southeastern Alberta, but all the way up to the really moist, productive grasslands west of Calgary, like in that previous slide I showed you with that exclosure, we're looking at over 180 tons of carbon per hectare. Now, most of that carbon was in the soil organic matter, and you can see that here in this black portion of the stacked bar graph. However, we found, interestingly enough, that there was a lot of carbon in the inorganic fraction as well, and also as a very significant amount in the dead vegetation. This is that thick mulch layer that's on the surface of the mineral soil that's in varying degrees of decay and decomposition. That's where a lot of your nutrient cycling originates from, and a lot of your carbon and phosphorus decomposition and so on is coming out of there. So this dead vegetation layer is a very important storage house of carbon, if you like. Now, we followed this up with some studies looking at nutrient cycling. And the reason for this is we wanted to know how quickly litter turns over, especially this carbon pool, and whether grazing impacts that. Well, interestingly enough, we looked at rates of litter decomposition in both long-term areas with grazing and in those exclosures where we removed grazing. And what we found is that we had accelerated grazing in the plant community, or accelerated decomposition in the areas with continued grazing. So interestingly enough, whether it's a priming effect because of the changes in the microbial community, or whether it's that hoof impact that Mackenzie was talking about with litter being incorporated into the soil, we found more rapid decay and decomposition. You can see that through these decay curves. The top graph here is for the foothills fescue. The bottom one is for the aspen parkland. In both of these, you can see that the grazed grassland tends to have greater rates of litter turnover or breakdown. Now, another thing that we did is we looked at rates of decomposition of different plant species. So we asked the question, well, do these different plants actually decay at different rates? And the answer is they do. For example, if you look at this graph in the lower left, you can see that Poa pratensis, which is Kentucky bluegrass, a very common agronomic grass that's grown on forages, particular for pasture, but also invades voluntarily into a lot of these grazed grasslands, actually exhibited the highest or fastest rate of decomposition. So it's turning over very quickly, which raises an interesting question. Where is that carbon going? Is it just being respired back to the atmosphere, or is it being broken down and incorporated into that surface soil, that particulate organic matter that Mackenzie was referring to? And so, and we also found differences in extracellular enzyme activity, which is some of the fundamental enzymes that microbes use to basically break down and turn over carbon, nitrogen, and phosphorus to facilitate their survival. Okay, so this is probably the most complex graph that I'm going to show you, but I think it is interesting because remember, we had data here from over 100 grasslands. And that enabled us to kind of mine through all of those sites and ask the very basic question, how is grazing, so grazing is this box here, how is it changing soil organic carbon, the mass of soil organic carbon? And this is called a structural equation model. You don't have to worry about the mechanics, but what's really interesting here is we found two significant pathways or mechanisms by which grazing can change soil organic carbon. The first one is that grazing, because it changes the plant community from being strictly dominated by the more competitive grasses, it allows for an increase in forbs. These are dicots, broadleaf plants that are generally moderately tolerant of grazing. Things like dandelion, strawberry, bedstraw, clovers. You can go on and on and on. There's dozens and dozens of them. But by allowing these broadleaf plants into the community and increasing their forb mass, that increased litter mass, which in turn increased soil carbon. So grazing boosts plant diversity, particularly these broadleaf plants, and that is one of the ways that soil organic carbon is favored. The second one runs through the graminoid component. So this is your main forages. You think of grasses. However, it wasn't being rooted through the graminoid biomass. So not the amount of forage, but the quality of the forage. Interestingly enough, we found that where we had grazing, it reduced the carbon to nitrogen ratio of that graminoid component. So it means plants that have a lower carbon to nitrogen ratio are more readily decomposable. They're higher in quality. They can break down more quickly through microbial action. And this increase in quality of graminoids again favored higher litter mass, which again favored increased soil organic carbon. Both of these pathways actually contribute to soil organic carbon increases. And the reason I'm really stressing this, interestingly enough, because Mackenzie pointed out the role of plant diversity, and grazing favors plant diversity. Okay, we have lots of data that we've published on that. Okay, another thing that we wanted to know is, some of you may have heard about Christine Jones. She's from Australia, and she's been arguing for this feedback cycle between grazing and the liquid carbon pathway, which is basically this pattern whereby plants give off root exudates, feed microbes, and then stimulate carbon dynamics in the soil. When I looked in the literature, I really didn't find a whole lot of specific information on whether and how this happens. So we actually did a study. This is Zilong Ma. He did an isotope study where he looked at carbon-13 labeling in grasslands subject to different defoliation intensities, and then looked at where did the carbon go? Where did it end up? So within 24 hours after the labeling event, 21% of the carbon was found in the mineral soil. So more than a fifth of the carbon had already moved into the soil within 24 hours. That's how quickly these carbon molecules are synthesized and then moved down into the soil. But from a grazing perspective, what we found was really interesting is that the grassland that was subject to more intense defoliation, so removing more leaf area, more biomass, those plants actually allocated more carbon to the roots within 25 days. So they're sinking or sending more carbon into the ground to support root maintenance, root growth, root exudation, and so on. And this could be a really important mechanism as to how and why grazing, when regulated properly, might actually stimulate soil organic carbon storage. Okay, so adaptive multi-paddock grazing systems. So these are these systems, and Mackenzie defined them, so I don't have to talk about them a whole lot. There's lots of pseudonyms for them: planned grazing, mob grazing, management intensive, high intensity, low frequency, regenerative, or even holistic. Not many producers are using them in Canada. Depends where you are, but anywhere from 3 to 10%. Mackenzie defined it really well. You take one big area, divide it into many smaller paddocks, which allows you to get higher animal densities. Okay, so higher animal densities at any one point in time, and then rotating them through. And it's the length of that rest period that really allows for plant regrowth and an increase in vigor and potential environmental and economic benefits. Okay, so back in 2016, there was a group of about 8 or maybe 10 of us that actually conducted an AMP grazing study. We looked at 32 operators in Manitoba, Saskatchewan, and Alberta that were using AMP grazing, and we looked at all kinds of responses, including forage production and use, water infiltration, carbon storage, greenhouse gases, microbes in the soil. We also documented all of the management activities. The reason we needed to know management activities, because the devil is in the details. If you're going to interpret what's going on farm, you really need to know what was done specifically in terms of how those animals were managed. Okay, we had broad regional coverage again, everything from some brown soils in the mixed grass prairie through a lot of kind of dark brown to black soils in the aspen parkland, foothills fescue, and boreal. So really broad geographic coverage and broad environmental conditions. And the way to think about this data set, I want to be really clear. Mackenzie described her study where she had a lot of control over the length of grazing and the exact specificity of the length of the grazing intervals, 1 day or 4 days or 8 days and so on. Because these are operational ranches and we always had an AMP operator and then we had the neighbor. The neighbor you can think of as conventional grazing, and in some cases they're continuous grazing. I once had someone with Alberta Environment describe this to me as the Columbus method of grazing. You turn them out in the spring and discover them at the end of the growing season, sometime in late October, and then you bring them back in. So that's season-long grazing, one paddock, no rotation, no individual pastures to facilitate rotation. But in other cases, we had AMP producers that might have been next to a slow rotational grazer. So instead of having 10 paddocks or 50 paddocks, they might have had 2 paddocks or 4 paddocks. So the study context here is important because the neighbors, when I say NAMP, those are neighboring operators, and they represent everything from close to AMP to moderate rotation to slow rotation to true continuous. Okay, I'm going to break down the results here into a series of questions. So the first one is, what are the management differences that existed? So this has been published. There were profound differences in the size of these operations. For example, the producers that had AMP operations where they were using these very intensive, aggressive, rapid rotation of animals tended to have much, much larger land areas. So close to 1,400 hectares instead of the neighbors that were usually around 300. So that might tell you something right away. And I believe the question was asked earlier is this going to require more management? It is. It absolutely is, because you need more infrastructure and you need more time and you need a willingness to move those animals. Of course, if you have a larger ranch, that means you're going to support a much larger herd size. And the difference here is represented logistically, that if you look at the AMP operators, they had a mean of roughly 60 pastures on their operation, whereas the neighbors had generally less than 10, and many of them had 3 or 4, very few. And of course, the pasture size is the opposite, where the neighbors basically had pasture sizes upwards of 120 hectares in size on average, whereas the AMP operators are dealing with much smaller pastures, somewhere around 20 hectares, okay? So big differences in the logistical layout and configuration of how these ranches were set up. Additionally, it's really important to note that the AMP ranchers were different in how they grazed, okay? But not necessarily how much they grazed. This is really, really important. So we know that stocking rate is the #1 cause of degradation on grasslands worldwide. It's the cause of desertification. With too many animals, overpowers the ability of plants to survive, they degrade, and you wind up with soil erosion and so on. So when you look at the aggregate stocking rate between the two treatments, AMP and the neighbors, there actually wasn't much of a difference. There was a little bit of a tendency for AMP to be higher, but it actually was not different statistically. Okay, they were quite similar. What did differ is how they grazed. The average stock density, so stock density is the number of animal units per hectare, was much, much higher, more than 20-fold higher under the AMP operations, as opposed to the neighbors. So AMP operators are using this herd effect that Mackenzie talked about, these really high animal densities to incorporate trampling and incorporation of litter and so on to their advantage. Now, this was also reflected in the timing of grazing. So AMP operators were able to start close to 3 weeks earlier than the neighboring operation. So a mean start date of April 25th, as opposed to May 17th. And the total grazing season was much longer under AMP grazing, around 7 months, as opposed to 5 months. So again, you can see what's happening here is that the AMP ranchers or producers are utilizing this special kind of grazing to extend the grazing season in the fall, extend it in the spring, and use that animal impact to their advantage. Now, we were able to use this information. We developed what was called a rest to grazing ratio, an RGR. And what you can see is that basically AMP ranchers strive to get this really long interval of rest after their pulses of grazing. And many of them were in for 1 day, some of them were in for 12 hours, but some of them stretched it out to 2, 3, or 4 days. But then they made sure there was this really long window of recovery before they would come back to it. Many of them were over 60 days. Okay, so this RGR could be a very useful tool. Now, the other thing I want to point out, okay, is that grazing, especially cattle grazing, is highly variable. I like to say we have 20,000 beef producers in Alberta, and there's 20,000 different grazing systems. So this is an ordination of the behavior of the individual ranchers in terms of their management metrics or tactics. You can see that the AMP producers are basically, the open triangles here are the AMP producers. The neighbors are generally clustered over here on the left side. But even among the AMP producers, you can see that there are marked differences in terms of how many pastures they had, the minimum rest period, and so on. There's this widespread distribution of management styles. So the implication of this is that categorical groupings of grazing management behavior are not really indicative of the real world, and that every cow-calf producer makes their own management decisions based on their objectives, their economic objectives, their landscape, their plant communities, and so on. So the use of these specific grazing metrics may actually be a much better way to explain and interpret cattle impacts on pastures, including things like soil carbon storage or even forage responses. So, and I think this has been one of the big flaws of existing work that has tried to look at regenerative grazing, AMP grazing, savory grazing, is that we try to use fixed experimental designs which fly in the face of how ranchers actually operate, which is using these variable and dynamic approaches. Mackenzie talked about that the management approaches in AMP grazing are not set in stone. That's important here. Okay, another really important question is, how does AMP grazing alter production, forage production? Now, we did not measure animal production. We would have loved to have, but we had 64 ranches at 32 locations, and it just was not possible to do that. But what we did find, this is very similar to some of the results that Mackenzie presented from the US, that AMP grazing actually led to greater grassland annual forage biomass production. And that was despite higher utilization. So this is one of those rare cases where we can have our cake and eat it too. We were getting upwards of 20% greater biomass production just by getting greater control over where, when, and how often and how intensely an individual plant was defoliated. They were, by giving them that extended rest period, they were regrowing, thereby generating more biomass. So, and this is probably one of the main vehicles through which we get more soil carbon storage, because unless your plants fix the carbon, you're not going to store more soil carbon. Okay. We also look at water infiltration, and Mackenzie mentioned this, and the Apfelbaum and that group was also involved in our study here. We found the exact same benefit, that AMP ranches basically had greater water infiltration rates, upwards of 50% plus higher or more rapid water infiltration, which means that during rainfall events, especially small rainfall events, or even really big ones where you're worried about overland flow, water running off, that these AMP grazed soils captured more of that water and made it available in the soil profile. So this, in water limited environments like Western Canada, this is really, really important, because anything we can do to get water into the soil and hold it there more quickly and more readily, that's incredibly important for mitigating drought effects and things like that. Okay, water infiltration, not surprisingly, increased with the rest to grazing days ratio. This is this minimum length of rest that producers implemented prior to regrazing. So producers that allowed for a longer rest generally had higher water infiltration rates. But also note the negative impact of stocking. So, and I want to be really clear on this, that when we talk about AMP grazing, this is really about how we're grazing our animals, how we're imposing defoliation on the pasture, rather than the amount of stocking. Because if you have excess stocking and you exceed the threshold, the tolerance of your plant community and your soil for that level of defoliation, you will degrade the community, you will reduce production, you will impair infiltration, and so on. So the real question is whether we can fine-tune our grazing with AMP type systems in order to get away with a modest, so a small increase in stocking rate. And I personally believe the answer is yes to that. Okay, we also asked this question of whether AMP grazing alters greenhouse gas emissions. So we did both field trials on this, and then we also did some incubation work, and I'll explain shortly why we did this. So what we did find is that our CO2 fluxes, so this is the amount of CO2 that's being released from the soil, did increase with total cattle stocking rates. So again, if we have really high levels of grazing, that's probably going to overwhelm the ability of that soil to deal with the change in environmental conditions. And then we're going to have this increase in soil respiration. The microbes are going to become more active, rather as opposed to what we're taking up through root exudates and root inputs and litter inputs. We did not find a difference in methane uptake on pasture. And I believe that methane uptake, I'm talking about the soil microbes themselves. However, I'll show you a slide shortly that suggests that there may be differences. What we did find is that when we compared grasslands that had a history of cultivation, that those soils, so you can see that over here in the graph on the right, the soils that were cultivated actually had higher methane, well, lower methane uptake or higher risk of methane release. So if you look at the y-axis scale here, these are all negative numbers. Negative numbers in terms of methane flux is a good thing. A lot of people are very surprised to find out that healthy soils have what are called methanotrophs. Methanotrophs are basically bacteria in the soil that consume methane. And a healthy soil, because of this methanotrophic activity, is actually scrubbing methane out of the atmosphere. And a lot of people are very surprised to find this out, because most people, when they think about cattle grazing, they just think of enteric methane production, which is cattle belching and then releasing methane to the atmosphere. But if those cattle are on a healthy grassland, there's also a significant amount of this methane consumption within the soil. Now, getting back to my point, those soils that had never been cultivated, that were still under the native plant community or these really high diversity plant communities with an intact microbial community, fungi, bacteria, archaea, and so on, those grassland soils actually had a more negative carbon flux. So that means they're taking more methane out of the atmosphere. That's a good thing. In contrast, those soils that had a history of cultivation at some point actually were a weaker sink. They were taking up less methane. Okay, I mentioned we did do some lab incubations as well. Now, the reason why we were interested in lab incubations is because we know that climate change is resulting in changes in temperature. And so we wanted to do some temperature sensitivity testing. So when we took soil from the field, from both AMP soil, and then the neighboring, you can think of the grazing treatment as having conditioned the microbial community. So that microbial community within each pasture is going to be kind of in a balance based on the inputs over time. So soils that were conditioned to AMP grazing had greater methane uptake. You can see that here, and you can see that here. The blue bars, AMP soils are actually have much higher methane consumption. Excuse me. And the other interesting thing is, when you look at the magnitude of that uptake, it was particularly large at high soil temperatures. Now, why do I say this? Well, in 2021, we had an incredible heat wave in Western Canada, And we had upwards of 34 to 37 degrees here in central Alberta for 2 weeks. That's unheard of. We normally have maybe 1 day above 30 degrees. That's it. So as we go through climate change and we get more of these heat wave events, raises this interesting question about what's going to be the ability of these soils to deal with greenhouse gas mitigation, including methane scrubbing from the atmosphere, this methanotrophic activity. Well, the AMP prime soils had higher methane consumption, and that could be a very good thing, especially at high soil temperatures. Okay, we did have a PhD student, Upama Katri-Shateri, who basically was looking at the microbial community. I'm not going to get into this in a whole lot of detail other than to say we have published results on this. And the answer is yes, the microbial communities are definitely different. For example, if you look at this graph here over on the left, the adaptive prime soils or conditioned soils had a lower microbial biomass carbon to nitrogen ratio. So again, this might be indicative of more active biochemical cycling over time. And we also see this effect of both stocking rate, that's this middle graph where you see again this shift in microbial biomass carbon to nitrogen with an increase in stocking, and how that grazing occurs. So the pattern of grazing. And the pattern of grazing is really representative of that stock density. Remember that herd effect, confining lots of animals into a small area to get more uniform use and then move them on so that the vegetation can then regrow. Okay, what about carbon stocks? Excuse me. Okay, so now this is the only paper thus far that we have not published yet, but showing some really interesting results. So when we look at the total soil carbon, and we did measure the carbon all the way down to about 1 meter in depth, you don't see a big signal. But what we do see are quite profound changes in the surface soil carbon, largely the top 6 inches or 15 centimeters. In particular, 2 things happened. One, you end up with a deeper, thicker topsoil. So the humified AH horizon. The second thing is that we find this net increase in soil organic carbon mass within the top layer. Now, excuse me, what's interesting here is that this increase occurred in relation to stocking rate, but only, so it was contingent on having these high rest to grazing ratios. So bottom line is, producers that were practicing AMP grazing, they had this really long rest to grazing ratio to ensure recovery. And only then did the higher stocking rate actually lead to greater soil carbon. And the way I'm going to describe this is like this. If you look at the graph here on the right side, a rest to grazing ratio of 0 is basically continuous grazing. It means there's no rest in between. This is the Columbus style of grazing. We throw animals in, we discover them at the end of the year. So under that framework, you can see that soil carbon actually declines as we push up stocking rate because animals are overusing plants. The plants are getting weaker in terms of their root systems, the leaf area, their production is being compromised, and therefore we're putting less carbon into the system. However, as you start to increase that rest to grazing ratio, so as you start to implement AMP grazing, what happens is that this curve from going negative actually starts to flip around and become positive. So the longer your rest to grazing ratio, the more likely you are to be able to benefit from higher stocking rates, enhancing soil carbon. Hopefully that makes sense. Okay, some summary points. Sorry. So grasslands are this really large storehouse of biological carbon. In my opinion, it's grossly undervalued by society for mitigating rising CO2. Hopefully, I've made a bit of a business case for the fact that our grasslands store this enormous amount of carbon. Secondly, that grazing alters this carbon pool, usually in positive ways, in part due to these complex dynamics of changes in plant biomass, changes in plant composition, changes in nutrient cycling, and so on. And AMP grazing is this very specialized way of aligning forage removal through grazing with the recovery of the plant community in the soil. AMP grazing can be another tool to enhance that plant productivity and soil carbon stocks. And in the end, we really need policy changes to fully value that grassland carbon. And in the process, incentivize livestock producers to maintain and even improve those stocks. Okay, here's a closing graph I want to leave you with. So this paper is not yet published, but I think it does maybe drive home this point. So in our benchmarking work that we've done, I mentioned we have over 100 locations where we have carbon stock data. So we took the carbon mass stock from those more than 100 sites, and we linked it geospatially to the land use footprint that Alberta Biodiversity Monitoring Institute has for the province. So this is basically a map that tells you what land uses are going on, including the footprint of grazing. And when we took our data and merged it with their data, we were able to come up with some really interesting conclusions. For example, across Alberta, we've got about 3.8 million hectares of grassland, and that contains more than 350 million tons of carbon. Okay, we also, because we had this land use footprint from ABMI, we project that grazing, which is occurring on the vast majority, more than 95% of these lands, has increased carbon stock by over 17 million tons. So just the fact that we still have grazing going on means we've sequestered 17 million tons of additional carbon. Now, what's that carbon worth? At a current value of 50 ton per CO2 equivalent, this carbon is worth over $3 billion with a B. So in my opinion, it's long overdue that we start recognizing the value of the carbon in these grasslands, including the additive role that grazing brings to the table. Now, this carbon valuation is not identical everywhere. So you can see the distribution in the graph here. The Aspen Parkland, which is this vast zone across kind of Calgary up to Edmonton over to Lloydminster, there's been an enormous increase in carbon there of about 8 million tons. The foothills fescue is another 4 million. The areas maybe that don't support as large a value add is the dry mixed grass. And that's because in a dry environment, it's really hard to add carbon because it's a water limited environment. And on the other extreme, the upper foothills grasslands are very small. These are within the Rocky Mountains, and they are by far the smallest in area. So it's not that we can't change carbon there. We can, but they don't cover a very large area. So the value add is maybe smaller. Okay, so with that, there's lots of groups that have assisted with this. I mentioned how many other researchers were involved in this. There's a lot of funders that have supported this along the way, including the Alberta Livestock and Meat Agency. Ag Canada, through their agricultural greenhouse gas program, supported specifically the AMP study that went on for 5 years. So with that, I see that I am exactly at 40 minutes. And so I'm going to wrap it up there, and I'm happy to take any questions.
That's fantastic. Thank you so much, Ed. That was really great. So if folks have any questions, please type them into the Q&A or into the chat. I just put in a link to the post-workshop survey, which I encourage people to also please take and let us know what they thought of the day. So I'm going to invite the rest of the panelists to come up and join us. So Shane Wood, Adam McLean, and Jonathan, if you want to turn on your cameras. And I'll introduce them, and then we can direct all of those questions to all of the panelists. So Shane Wood is the forage specialist and lead research coordinator for Agri-Services at Perennia. As the forage specialist, he provides advice on best management practices for hay and silage production, as well as pasture management to producers in Nova Scotia. And he'll be working on forage small plot and on-farm research. Shane enjoys helping producers to find ways to increase their farm's profitability and sustainability. Adam McLean is a first-generation shepherd and grazier operating in the hills of South Melville, Prince Edward Island. Adam shepherds his flock of 200 ewes outdoors year-round, relying on hedgerows and spruce woodlots for shelter and livestock guardian dogs for predator protection. He employs adaptive multi-paddock grazing to improve soils, extend the grazing season, decrease operating costs, while keeping the flock productive and healthy. Adam also works as the Agriculture Climate Action Specialist with the PEI Department of Agriculture and Land. And then our moderator today is Jonathan Wart, who is Perennia's Manager of Livestock and Field Crops. Many of you might know him from when he was our beef and sheep specialist at Perennia for over a decade and a half, maybe, Jonathan. And before that, he was a beef and sheep farmer for 25 years. So with that, Jonathan, I'm going to turn it over to you to facilitate.
Yes, good afternoon. I think we've had a pretty impressive day and a lot of information exchanged hands. And, you know, from my perspective, I mean, I'm obviously very interested in the grazing management and the information that both Mackenzie and Ed have shared with us. And I guess, do we have any questions that anybody wants to put on the table? And I can't imagine Adam doesn't have some comment or thoughts related to this issue.
Well, you know, Jonathan, I'm a proponent for adaptive grazing. I still blame Jonathan for pushing me over the edge and committing to sending a check to a shepherd in Ontario to buy my first flock of sheep. So depending on the day, that's either a positive thing or I'm cursing your name. I guess I could speak less from the specialist perspective, but really quickly from the practitioner's perspective. And this might be helpful whenever communicating with farmers who are grazing curious, but what's in it for the producer is not necessarily carbon sequestration so much as more forage, more drought resilience in the landscape. The ability to manage your forage volume through the season is essential. To be able to take your spring flush of growth and meter that out through your summer slump, and then take your early fall growth and manage that through late fall into winter grazing is really invaluable. Anything to be done to extend the grazing season to reduce the days on stored feed, especially with the price of diesel where it's at right now, the price of silage wrap, that's going to be a motivating factor that speaks to that farmer's direct benefit. One other opportunity there is just the potential to put on or to manage average daily gain. And the complaint is often the labor cost. Fortunately, OFCAF is there to help offset some of the costs of making those infrastructure investments. And through good design, there's the potential to manage those labor costs. And you know, it's the best part of the day, moving animals from one paddock to the next, and a lot to be learned whenever you're seeing who's consistently the last through, what forages are those animals eating when they move to a new paddock. There's a lot to be learned, and it is a good opportunity for a new entrant or a first generation operator like myself to really increase the amount of time with animals and observing animals and forages. And with respect to don't let the perfect be the enemy of the good, like there's a lot of deep science here. There's a lot of different practices. Just buy a geared reel and some polywire and some fiberglass posts and try splitting a paddock, you know, just split it once and just start to observe the interaction of the animals with the landscape. And there'll be mistakes made, but just by getting into that practice of observing and interacting with forage animals and grazing a bit more often, it's the beginning of a journey that should lead to some interesting places.
So there's a couple of questions here that people have brought up. So the first one is, Ed kind of addressed this in his talk, but would be good to reiterate. One of the off-calf BMPs is to establish the establishment of low methane pastures. And kind of what does that mean to you, Ed?
Wow, that's a good question. Methane from the perspective of the animal or the soil. So there was a point raised earlier about forage quality. And what we do know about animals, like we're not measuring methane from the animals per se, although we are we are doing some work on precision ranching right now where we're looking at methane emissions from cattle under open range grazing. And we're trying to figure out we're trying to figure out a way to non-invasively characterize their diets and then look at their feed efficiency and their cow-calf production and so on. But that's another story. But what we do know is that if you have an animal taking in a lower quality plane of nutrition, their methane emissions are higher. So if we can strive to maintain a higher baseline diet for an animal throughout as much of the grazing season as possible, that should reduce at least the enteric methane footprint from that animal over time. Now, one of the arguments is that under AMP grazing, because you're getting more uniform use of all the forage plants within that individual paddock, you're maintaining that regrowth pattern over time. You're resetting that phenological development on the plant. Then in theory, now moisture permitting, if you're in the dry mixed grass and you don't have moisture to facilitate regrowth, you're hooped. But if you have enough moisture to enable that regrowth to occur, then you should maintain a higher plane of nutrition for a longer portion of the grazing season, in which case your enteric methane footprint should go down. So, again, that's another win. And I agree totally with you, Adam. If right now producers are not getting paid a premium for storing carbon or reducing their greenhouse gas emissions, that's not what they're being paid for. They should be, but they're not. I mean, at some point, we need to kind of rethink that paradigm, or support biodiversity and filter water and purify water and provide wildlife habitat, all of those things. But that's another workshop altogether. But in terms of the soil itself, I've probably done half a dozen media hits in the last 2 years, and I'm stunned at how few people, even producers, are not aware of the fact that a healthy soil is on average a net methane sink. Okay. And this makes sense to me, given that we know very little about the soil microfauna. And when you start getting into the complexity of these systems, there's a lot more functioning that's happening below ground under our feet than we've come to kind of accept up until now. The other thing that perplexes me from a social perspective, and from a social license perspective, I guess is a better way of putting it, we don't necessarily have to have, because I get this question, is my soil, if it's really healthy, taking up enough methane to offset the enteric methane? It's not. I don't think so. I've done a back of the envelope calculation, and I think it's about 25%, which is not bad. That means we're offsetting 25% of what we're releasing from the animal through enhanced methanotrophic activity. But I would argue, well, wait a minute, let's wind back the clock. Here in Western Canada, we have tens of millions of bison that were running around. They were functionally pretty similar to our cattle, and they were producing methane, and yet the planet wasn't spiraling out of control through climate change. So I'm pretty sure that if it was sustainable back then, it can be sustainable now, and we don't have to point the finger at cattle and say they're destroying the entire planet. So to me, the devil is in the details of how we graze, and looking at that accumulative footprint of what those animals are doing, and whether it's through biomass production and carbon sequestration, the way I showed with what we're seeing in Alberta and across the prairie provinces through increased carbon storage, or a part of which is methane uptake. I think those are all very positive news stories. We just haven't gotten that good news story out there, in my opinion.
Yeah, I think we need to do a much better job communicating, the story that we have to tell about the impact of grazing and what our livestock are doing. So the next question is, AMP sounds like it involves a lot more management decisions and harder to make an actual grazing plan. Could the various panel members comment on that? Mackenzie looks like
I just want to echo what Adam said. Start out simple. I mean, we're doing that now because we're starting our living lab here in Alberta in conjunction with the Alberta beef producers. And the one thing that I do not want producers to do is to jump in and try to swim across 10 miles of open water. I don't think there's any point to doing that. And I think we have seen that in the past without naming names, but there's been producers back in the 80s that jumped into kind of, well, holistic grazing and said, I'm going to double my stocking rates because that's the way to go. And I know I can make it work. And then when they crashed out, it wasn't because the system failed, it was because they doubled their stocking rates. And so start out simple. I agree with you, Adam. Build one cross fence, then 2, then 3, then 4, and you will quickly figure out where the law of diminishing returns takes you and where your optimum is.
And grazing plans aren't nearly as important as grazing planning. So if you're running a scientific study, you need a plan because you need consistency, you need to reproduce results. But a plan is not going to do anybody any good because plans change as soon as precipitation changes. It's the act of planning, observation, that's most important.
Some of that is, just to echo that, it's about having flexibility is really what you need to have to make this work. It's nice that it's good that to have thought through the process and how you're going to handle things as they come along. So in that, there's value in a grazing plan in that sense, but realize that you may have to throw it all out the window and come up with a new plan on the fly, depending on what's going on that year.
Yeah, just to add to that a little bit, that's why I tried to focus on the functions that facilitate all of the good things happening with improved grazing and not necessarily specifically exactly what you should do. So yeah, I agree with all of what's said. As long as you have an understanding of that, then those other things will come.
Okay, so let's go to the chat, see what we have here. Nicole asks, knowing that there's no grazing in the winter, what's the overall greenhouse gas budget when raising beef? I don't know if anybody can comment on that or not.
I can't comment on it except to say that through bale grazing, there is the opportunity to reduce the diesel costs of manure management significantly and the potential to have manure drop where it needs to be. So when that snow melts in the spring, it's on rapidly growing grass. Your urine is on grass that's going to be growing as well. So you can say there's no grazing in the winter, but there's also the possibility to do winter bale grazing in terms of laying out winter supply of forage in advance on your weakest fields. It's my fertility input strategy for my weakest fields where I'm looking to rebuild fertility, is to bring in those bales and then move those animals through that space.
And Keith asks, where's the balance between longer rest periods and harvesting pastures while still vegetative to maintain feed quality? Is there a point where the benefit of more soil carbon is negated by the higher enteric methane?
I don't think there is. So there's that flexible, the need to be flexible again and trying to figure out when we did our AMP study, we spent a lot of time crafting the survey of producers because we wanted to get the specific mechanics of what producers are doing. And it's always tricky because if you make the survey too long, you bore them and then they don't really want to do it, or they just want to get it over with as quickly as possible, as opposed to giving us really useful metrics. But here's the impression I got, and Adam or others can jump in and just say. So here in Western Canada, we have this very differential kind of phases that we go through. We go through the time of plenty when we have lots of growth and really high quality, and it's explosive growth that occurs for 6 to 8 weeks. It's the easiest time to make a living if you're a livestock producer because there's loads and loads and loads of forage. In fact, you run the risk of wasting forage if you're not careful of how you use it. Because so what you really are trying to do, you're trying to make sure that forage gets used and that you reset the plant successional development clock, the plant phenology. And a lot of producers were very attuned to that. Now, granted, if you have a drought year, that time of plenty goes really quickly. It might be only 4 weeks or 5 weeks. And if it's a really wet year, it might be 9 or 10 weeks. So there's that balancing act, but most producers had figured it out. And so if they have, 60 paddocks and they're going through at 1 paddock a day, that after 60 days on average, they know they've reset the successional clock on all those pastures. The next phase is a little bit trickier because what you wind up with is lots of biomass in the late summer and fall, but quality is lower. And so then it becomes a matter of getting what we call efficient harvesting, which is your animals making sure that you get efficient intake of that material so that you're not getting this real patchiness of use, right? And the longer you can extend that into the late fall or even into the winter, and some of our producers here in Alberta are grazing 10 months of the year just through really careful stockpiling and planning. Now, they have to have a reserve of feed because you never know. You can get one of these winters where you wind up with way more snow that you would have expected. But that's the art. Range management and grazing management is an art and a science. The science is using the best information available. The art is applying it to your unique land base for your soil, your vegetation, your watershed, your drainage, and your economic objectives. So going back to that question, there isn't going to be one exact grazing system that works everywhere. And that, I think, is the fundamental flaw, to pick on my fellow researchers. That's why a lot of these studies have failed, because they use these really rigid designs. And as soon as you do that, you've taken out the very adaptive, flexible nature of the system that makes it successful.
Also recognizing that, different stock classes, there are different grazing strategies for different stock classes. I will use dry ewes to do weeding and eat some over mature forage that I, left earlier, whereas my lambs, as much as I can within parasite management responsibilities, we're aiming for vegetative growth. So it's never either or, this strategy or that strategy. All strategies are on the table at all times, and sometimes at the same time, depending on the goals of the production system.
So another question, or I guess we're looking for some importers' thoughts on development of satellite collars and kind of what people know about it, especially in light of the hurricane damage that we experienced. A lot of producers had significant fence damage, and I guess we really talk about intensifying grazing, and that relies on more fences or some kind of fencing technology. And kind of what are your thoughts, and where do we stand with the technology? Do any of you know anything about that?
I do. We are using virtual fencing actually in a research trial right now. So we started using it just this past summer in 2022. We had 49 heifers and 2 bulls that were fitted with virtual fencing collars. This is No Fence, which is out in Norway. And we had some initial problems last winter and spring, not with the platform. The platform works really well. So this is basically a collar. It's like a dog shock collar, but it goes on a cow. And so the collar is solar charged. So basically you charge it up initially, and then it takes, light on. And basically we're still running them, by the way. We just removed them a week ago and they were still running. They were still operating. They were still getting enough light, which is incredible for how far north we are here in central Alberta. The initial problems we had were with the cell connectivity, which is needed because you run the entire platform from your cell phone. You program the pastures and they're dynamic. You can change them in real time. So, and what we use them for this summer is just to train the animals. Work great. The cattle learn very quickly to use these things. They figure it out. And then we also used it to implement a simple rotational system. So we took existing permanently fenced paddocks and split them either into 2 or 3 paddocks, and it worked really, really well, where the animals knew they would get up, they go up to a virtual edge, they get an audio cue, and then if they keep going, they get 3 audio cues, and then they get a shock. And it doesn't take long. They figure out very quickly that that's not something that they want, and they turn around. So next year, we want to expand the trial to look at this on cow-calf pairs. So because you only want to put a collar on the cow, then the question is, are the calves going to represent a distraction? Because the calves could wander further away from the cows. And so that's another incentive for the cow to maybe break the barrier, right? And to go retrieve their calf. So that these things are not cheap, I'll tell you that. But what I do believe is going to happen is that as the technology becomes more useful and the applications become more clear, I think the cost is going to come down per unit. And you're going to see more manufacturers that are going to jump in and start to build this technology. So I think it's very encouraging. You could do riparian area exclusion. They're even using them in Europe to herd them away from water in the morning, and then they herd them back to water in the evening. It's incredible what they're capable of doing.
So we have a question for, thank you, Ed. I've been fascinated by this technology ever since I saw it first, probably 4 or 5 years ago, and it doesn't seem to be, it seems to be slow to be moving into North America. And I'm not sure why, but maybe it's slow being adapted around the world too. So Ryan asks, what are some of the best solutions for getting water to multiple paddocks? And I guess that's a big question, and I'm not sure there's a simple answer.
There's no simple answer. It's going to vary so much on the landscape, the farm, the particulars. But Ryan's hit on, everybody focused on the fencing requirements, and the fencing requirements, even the cost of it can be minimal compared to water. So depending on the lay of the land, there may be springs, the ability to develop, gravity flow to a header tank, gravity flow out of that, solar pumps, and then there's the solution of a well on mains power. And poly pipe prices add up fast, but that's an advantage of the off-calf program for those who are willing or ready to take the jump. Poly pipe is a miraculous technology to move water pretty good distances. In the winter, for sheep anyways, snow is usually sufficient if it's the right quality and texture and of snow to provide for the water needs of livestock.
So let's see, Keith has asked, where's the balance between a longer rest period, harvesting pasture while it's still vegetative to maintain feed quality? Is there a point where the benefit of more soil carbon is negated by the higher enteric methane?
I think as long as you balance off what the animals need with what your pasture needs to maintain really active growth and maintain quality, you are going to sequester, you're going to produce more biomass, you're going to allow your animals to harvest more of that biomass, and you're going to put more weight gain on. But there's no exact rule. The best way for me to answer that is go to the extremes. If you practice the Columbus style of continuous grazing, your animals are going to utilize 20% of your pasture. At 80 to 90%, the vigor of those desirable forage plants is going to go away. Those plants are going to eventually disappear, and you're going to be eating weeds. That's what's going to happen. Whereas if you start dividing that into much smaller areas, you get more uniform utilization, you retain and keep the more productive, desirable forage plants. And because they're allowed that recovery period that they need to maintain productivity, you are going to get more biomass within one growing season and certainly between growing seasons over time. So, it is an art form. If I'm working with a producer at Medicine Hat in southeastern Alberta, where they get 300 millimeters of rain and they have a growing season, an effective growing season of 2 months, and then they're stockpiled already, in July 1st, that's a different discussion than if I'm north of Edmonton at Barhead, where they're getting 500 millimeters of rain, and they have the cup runneth over on moisture and regrowth potential. So every single context, operation, night and day different conversation between those two individuals. So it really depends on where you are, what your goal is, and how much time you want to put into this. That is not a trivial question.
Thank you. We do have one last question, I think. Are the collars commercially available yet, Ed?
Sorry, was that, are the collars available yet?
Yeah, commercially available for purchase.
They're not available commercially yet. The company I'm dealing with, there are several globally. The company that I'm dealing with is still kind of rolling out and trying to target in North America researchers to show the value of the product. But I anticipate that once that's done, that will be forthcoming. I know here in Western Canada, there are even, like TELUS has started their own development effort to produce these collars as well, their own collar. So you can see what's happening. As soon as there's a market opportunity, other companies are going to jump into this. And I know one of the local tech schools, the Northern Alberta Institute of Technology, they're talking about developing potentially a collar themselves. So you can see what happens. As soon as there's a need for it and a demand for it, it will come. I hope sooner than later, because I do think it's a very useful tool.
Well, it's like a lot of things. Once it gets adopted and people start using it, the price will probably come down, hopefully.
Yeah, I agree with you. And that's they're not cheap right now. They're quite reliable. We haven't had one fail throughout the entire summer. Not one has failed, which is impressive at this point. The GPS is really high quality. So, and what we anticipate is that the price will eventually come down. Both the price per year, because there's a subscription fee for the cell connection and all of that kind of thing, plus the collar.
Sounds like you might have better cell phone service in Alberta than we have in Eastern Canada and places.
Depends where you are. We were doing this on a ranch 140 kilometers outside of Edmonton, and we had a heck of a time in March and April, and we were thinking we weren't going to be able to run the trial. And then our provider, our tech provider, had to reach an agreement with, so our initial agreement, their in it, not mine, but their initial agreement was only with Rogers. So our coverage was not that great. But as soon as they entered another agreement with, I believe, Bell and TELUS, then, because there's so many towers, but we were only accessing a fraction of them. So as soon as they did that, the technology worked just fine. So a lot of this is, was international level dialogue that was out of our control.
It's, yeah, maybe it'll actually drive improved cell phone service if we get enough cows out there with collars on them.
I agree. That might happen.
Anyway, we do have a question here from Brock, and it says, do you think these collars would be cheaper than automated fencing? I've been seeing some producers talking about using those for, I'm assuming, rotational grazing, RG. Yeah.
I don't know what automated fencing is, because the virtual fencing is about as close as you're going to get to automated fencing, because you can basically move them from your pickup truck or your living room if you want.
Yeah.
I'm thinking maybe he's referring to bat latches, or I've seen polywire lifters, which could be a good interim solution, but nothing's going to be as automated as GPS guided collars. But given that technology is probably not going to come down fast enough for a flock of sheep, or do I want to be shearing the shock collar spot? Might have to stick with bat latches.
No, but what might be interesting is, what if you had a handful of lead animals that you could put a collar on, and then you influence the lead animals and everything else follows. So that would be interesting.
It's interesting technology, and I guess there's probably a lot of opportunity to just do some research into animal behavior. So I think we've come to a little over our time period, and we've had some good questions. I want to thank everybody for participating. Rosie, are you still there?
I sure am. I was just signing on to say that it was 5:05, and I think some people might want to go home, but you guys, this has been absolutely great conversation. Thank you so much, Ed, for joining us from afar, and Shane and Mackenzie and Adam and Jonathan for lending your regional expertise. Very much appreciated. So again, I've put the survey, the post-workshop survey in the chat. I will harass you by email as well to fill that out. Your responses are really important to us in making sure that we are offering educational things that are meeting your needs. So thank you again, everybody, for your participation, and safe home.